Hello everyone, I am Bharat Singh Irom from Tezpur University, Department of Food Engineering and Technology. Today I am going to give a presentation on spray drying in food processing under the guidance of Dr. Sarulata Mahanta, Professor, Department of Food Engineering and Technology. Here are my table of contents for my presentation. Introduction, importance of spray drying, limitation of spray drying, principles of spray drying technique, basic steps of spray dryers, factor influencing the properties of fruit juice powder produced by spray drying technique, application of spray drying in the production of food powder, advantages of spray drying, disadvantages of spray drying, trends in spray drying, conclusion and references. In introduction, spray drying involves dehydrating finely atomized or spread droplet in a hot convective medium, converting the droplet into fine solid particles. The key advantages of this process is the ability to dehydrate the liquid material and to simultaneously produce the material in a micronized particle form. Depending on the spray drying process used, the particle produced can come in different sizes. Table 1 shows the typical particle sizes from various spray drying configuration and fit properties. Some food particles are skin-forming and hollow, which often leads to shriveled-up structures as shown in Figure 1a and 1b. In such hollow particles, different particle surface structures can also be produced depending on the operating parameters of the spray dryer, as shown in Figure 1c and 1d. Figure 1a and b shows about the shriveled particles, c about the particles with spherical internal void, and d about hollowed and non-shriveled particles of spray-dried particles. Smooth surfaces can also be produced by spray dryers as shown in the Figure 2. However, this is rare in the case of powders produced by large commercial dryers. Figure 2 shows about the smooth spherical particle structures and 3 about the agglomerated spray-dried powder particles. Importance of spray drying. Spray drying is regarded as the most economic drying technique due to its low operational expenditures. According to the report of Hamami and Rene in 1997, an industrial-scale comparison showed that the spray drying process is around 4 to 5 times more economic than that of the freeze drying due to its less electricity consumption and short drying time. Santi Bargna and its team in 2007 reported that spray drying is 8 times more economic than freeze drying and 4 times more economic than that of vacuum drying. Spray drying includes the benefit of relatively short drying contact time, that is between 5 and 100 seconds, and therefore tends to preserve sensitive quality attributes, for example nutrients, color and flavors. The spray dried product is highly stable because of its low moisture content and water activity. Common ranges of moisture content and water activity of spray dried fruit and vegetable powders are 2 to 5% and 0.2 to 0.6% respectively. Limitations of spray drying. It involves relatively high drying temperature, typically 150 to 220 degrees Celsius of inlet air temperatures and 50 to 80 degrees Celsius outlet air temperature, as suggested by Fishwood in 2012, which can damage sensitive compounds, that is lycopene, beta-carotene, anthocyanins, vitamin C, colors and flavors. Fruits and vegetable juices are difficult to directly spray dry without a carrier agent due to their stickiness behavior and low glass transition temperature, which leads to wall deposition problems and drying difficulties. The control of droplet size in spray drying is limited, leading to particles of board size distribution and sometimes irregular microstructure, as suggested by Dalmoro and its research team in 2012. The thermal efficacy of spray drying is comparatively low because hot air circulates in a large volume of spray drying chamber with no contact to spray droplets. Principles of spray drying techniques. There are 3 fundamental steps involved in spray drying. The first one is atomization of a liquid feed into fine droplets. Second, mixing of these spray droplets with a heated gas stream, allowing the liquid to evaporate and leave dried solids. Lastly, dried powder is separated from the gas stream and collected. Spray drying involves the atomization of a liquid feedstock into a spray of droplets and contacting the droplets with hot air in a drying chamber. The sprays are produced by either rotatory or wheel or nozzle atomizers. Evaporation of moisture from the droplets and formation of dry particles proceed under controlled temperature and airflow conditions. Powder is discharged continuously from the drying chamber. The first spray dryer were manufactured in the USA in 1933. The gas generally used in spray drying is air or more rarely an inert gas, particularly nitrogen gas. Let's discuss about the spray dryers. The spray dryer is a device used to produce dried foods. It takes a liquid stream and separates the solid or suspension as a solid and the solvent into a vapor. As shown in the figure 4, the solid is usually collected in a drum or cyclone. The liquid input stream is sprayed through a nozzle into a hot vapor stream and vaporized. A nozzle is usually used to make the droplets as small as possible to maximize the heat transfer and rate of water vaporization. Figure 4 shows the overall illustration of the spray drying process. Droplets enlarged to illustrate the particle formation. The spray dryer can also turn a solution or slurry into a dried powder in a single step, which can be the advantage for maximizing the profit and minimize the process. Now let's get some information about the basic steps of spray dryers. The basic steps of spray dryers include the concentration of feedstock, atomization, droplet air contact, droplet drying, separation of dried particles, and the carrier agent. Concentration of feedstock. The feedstock is concentrated before introducing into the spray dryer. The concentrated juice of the feedstock has increased in solid contents, thereby reducing the amount of liquids and that must be evaporated in the spray dryer. The feedstock in the conventional large-scale spray dryer normally concentrates to 50 to 60% before introducing to spray dryer. Atomization. Atomization refers to the conversion of bulk liquid into a spray or mist, often by passing the liquid through a nozzle. Droplet size ranges from 20 micrometer to 180 micrometer and it depends on the nozzle. The aim of this stage is to create a maximum heat transferring surface between the dry air and the liquid in order to optimize the heat and mass transfer. Droplet air contact. The important component of spray dryer is the chamber. Here the sprayed droplet is contacted with the hot air and the drying process begins. Air is heated by the heating element which is situated before entering the chamber to a predefined temperature depending upon the characteristics of the feed fluid. The hot air is brought in contact with the spray droplet in the following ways through the air distribution system. Co-current air distribution system. In this system, the air and the particles move in the same direction with inlet temperature of 150 to 220 degrees Celsius. Counter-current air distribution system. In this, the air and the particles move in the opposite direction. Lastly, the mixed flow. In this system, the particles are subjected to co-current and the counter-current phase. The hot air evaporates moisture content in the droplet and changes into powder form. Figure 5 shows the typical spray dryer configuration with co-current, counter-current, and mixed flow air distribution system. Droplet drying. At the stage of droplets, hot air contacts between the liquid and the gas phases and balances the temperature and establishes the vapor partial pressure. Heat transfer is carried out from the air towards the product and thus induces the differences in temperature. Water transfer is carried out in the opposite direction due to the vapor pressure difference. Figure 6 shows about the convective heat and mass transfer and the solidification process in spray drying. As shown in the figure, droplet heating dependent on drying rate, droplet temperature, hot air temperature, droplet air relative velocity, size of the droplet, and droplet thermal properties. And moisture loss is dependent on droplet moisture, droplet temperature, hot air humidity, droplet air relative velocity and size of the droplet, and also the particle solid formation dependent on drying history, droplet composition and material, and droplet moisture. Separation of dried particles. This separation is often done through a cyclone placed outside the dryer, which reduces product loss in the atmosphere. The dense particles are recovered at the base of the drying chamber, while the finest ones pass through the cyclone to separate from the humid air. Carrier agent. The problem of powder stickiness is mainly due to the low glass transition temperature of the low molecular weight sugars present in such products, essentially sucrose, glucose, and fructose. The low glass transition temperature, high hygroscopic, low melting point, and high water solubility of the dry solids produce the highly sticky products. The common carrier agents used for fruit juices are maltodextrin and gum arabic. Gum arabic is natural plant extruded of acacia trees, the only gum used in food products that shows high solubility and low viscosity in aqueous solution, making easier the spray drying process. Now let's see about the factors influencing the properties of fruit juice powder produced by spray drying technique. The factor consists of inlet temperature, air dry flow rate, atomizer speed, feed flow rate, type of carrier agent, and the concentration of the carrier agent. Inlet temperature. Powder properties such as moisture content, bulk density, particle size, hygroscopicity, and morphology were affected by inlet temperature. Normally, the inlet temperature used for spray drying technique for food powder is 150 to 220 degrees Celsius. At higher inlet air temperature, there is greater temperature gradient between the atomized feed and the drying air, and it results the greatest driving force for water evaporation. Additionally, the inlet temperature affects the bulk density of powder. An increase of drying air temperature generally causes the decrease in bulk particle density and provides the greater tendency to the particles to hollow. The inlet temperature can also affect the particle size. The use of higher inlet air temperature leads to the production of larger particles and causes the higher swelling. When the inlet air temperature is low, the particle remains more shrunk and smaller. The inlet air temperature has a role on the hygroscopicity of powder. The higher drying temperature is lower the moisture content and increase its hygroscopicity, its capacity to absorb ambient moisture. Furthermore, the inlet temperature also influences the morphology in acai juice powder. When the inlet air temperature was low, the particles showed a shriveled surface, while increasing the drying temperature resulted in a large number of particles with smooth surface. Figure 7 shows the micrographs of particles of acai juice powder at different temperatures and in different magnification. As we saw in the figure, the particle structure ranges from shriveled structure to the smooth surface structures with different combination of inlet temperature. Air dry flow rate. A lower drying air flow rate causes an increase in the product halting time in drying chamber and enforces the circulatory effects. An increase of the drying air flow rate decreases the residence time of the product in the drying chamber, and it leads to have higher moisture contents. The rise of air flow rate leads to an increase of moisture content in the powder and decrease in the powder bulk density. Atomizer speed. Sezzini and Govadian in 2005 studied the effect of atomizer speed 10,000 to 25,000 rpm on the properties of an orange juice powder. The residual moisture content was decreased when increasing the atomizer speed. At higher atomizer speed, the smaller droplets were produced and more moisture was evaporated, resulting from an increased contact surface. The higher atomizer speed resulted in a small particle size and quicker drying due to the large surface area and consequently in preventing the skinning over the droplets. Feed flow rate. It negatively affected the moisture content in the acai juice powder. Higher flow rates imply in a shorter contact time between the feed and the drying air and making the heat transfer less efficient and thus cause the lower water evaporation. Type of carrier agent. The addition of higher molecular weight additives to the product before atomizing is widely used as an alternative way to increase glass transition temperature of powder. The use of carrier agents such as maltodextrins, gum arabic, waxy starch, and microcrystalline cellulose was influenced the properties and stability of the powder. The highest amorphous fraction was found in powder added with the gum arabic. Gum arabic has a higher glass transition point due to its larger molecular comparing to other carriers. Therefore, the powders produced by arabic gum showed the less amorphous behavior during spray drying when compared with the waxy starch and maltodextrin. Figure 8 shows the effect of carrier type or microstructure of powder with gum arabic, waxy starch, and maltodextrin at 12% respectively. Concentrations of carrier agent. The concentration of the carrier agent also affected the powder properties. Low concentration of carrier agent may obtain the stickiness powder. Maltodextrin was mainly used in the process of spray drying due to its physical properties such as high solubility in water. Grabowski and its research team in 2006 also reported that the water solubility index of sweet potato powder increased as the amount of maltodextrin increased. Now let's see about the application of spray drying in the production of food powder. Dairy powders. Material migration during spray drying. During spray drying, as the droplet loses moisture from the surface, the solute concentration at the surface becomes very high, creating a solute concentration gradient across the radius of the particle. This solute gradient causes the solute or suspended materials to diffuse inwards into the droplet. Due to the significantly different diffusivities, lactose, which has the highest diffusivity, will migrate inwards faster into the droplet, followed by the proteins and the fat molecules, due to their relative difference in diffusivity. This explains why the surface of full cream milk powder is overrepresented by fat. What is the implication of having high surface fat content? Firstly, surface fat are exposed to the ambient condition, which makes it vulnerable to oxidation. Oxidation of these fats will affect the quality of the product. Another problem rising from surface fats is the stickiness problem. At higher temperature in spray drying, the fat component might soften, leading to a sticky vertical surface. In view of the slow dissolution behavior of fat containing dairy particles, agglomeration of these particles in second stage fluidized bed drying is a very common practice to improve the dissolution rate of these particles. Agglomerated clumps exhibit large voids within the agglomerates, which will then enable better penetration of the dissolution water to contact the particles. This method can also be used for other instant food particles. Figure 9 shows about the agglomerated skim milk powder. Prediction of the drying behavior of dairy products. Typical in spray drying is the presence of a constant drying period in the initial condition when the droplet is still saturated with water, and the falling rate period in which the drying rate deteriorates due to reduction of surface moisture. It is now possible to predict the proportion of fat, protein, and lactose accumulated on the surface after spray drying, depending on the initial dairy feed composition. Food powder with high starch or sugar content. Stickiness is a prevalent problem in the spray drying of food powder with high starch or sugar content. Why does this stickiness issue arise? This is because the dissolved solids do not have sufficient time to reorganize into stable crystalline or ordered structures under the short drying time. One way to overcome this amorphous problem in food powder is to adjust the glass transition property of that food powder. Non-stick chamber wall. Using a non-sticky hydrophobic Teflon wall material, reduction in maltodextrin sucrose particles was observed in a pilot-scale spray dryer by Adhikari and its research team in 2007, Wu and its research team in 2008-9. However, it was found by the latter authors that the reduction is more significant when the particle is rubbery. On the contrary, This effect was found to be not significant for skim milk powder by Kota and Langris in 2006. High protein products. A major issue in spray drying high protein product is the denaturation phenomenon, in which the spray dried protein loses its ternary structure, leading to loss of functionality. This phenomenon is mainly due to the thermal stress imparted onto the product during spray drying. Denaturation occurs significantly mainly in the preheating and pre-evaporation stage to concentrate the dairy solution for spray drying. Encapsulated powder. One application of the encapsulation technique is to retain high volatiles and fragrance in food products. Another application is to prevent the exposure of the sensitive materials to the environment by encapsulating the materials within the matrix of the particle. One example of such an application is the encapsulation of fish or high-value oil droplets in particles to prevent oxidation upon exposure to the environment. Here are some advantages of spray drying. The process is very rapid, with the major portion of evaporation taking place in less than a few seconds. Adaptable to fully automated control system that allows continuous monitoring and recording of very large numbers of process variables simultaneously. Wide ranges of spray dryers design are available to meet various product specifications. Powder quality remains constant during the entire run of the dryer. Nearly spherical particles can be produced, uniform in size and frequently hollows, thus reducing the bulk density of the particle or the product. Offers high precision control over particle size, bulk density, degree of crystallinity, organic volatile impurities, and residual solvents. Disadvantages of spray drying. In spray drying, the equipment is very bulky and with the ancillary equipment is expensive. The overall thermal efficiency is low as the large volumes of the heated air pass through the chamber without contacting a particle, thus not contributing directly to the drying. Here are the trends in spray drying. Number 1 is ultrasound assisted spray drying. It comprises of 3 sub-steps. The first one is atomization system. It consists of a piezoelectric actuator driven at an ultrasonic frequency of 60 kHz, producing a fine liquid droplets with uniform size. The second is drying chamber. It consists of a glass dry post with a laminar air flow leading rapid dehydration of droplets into dehydrated microsphere using a moderate drying unit. Lastly, electrostatic particle collector. It comprises a star electrode or cathode and a tubular particle gathering electrode or anode with high voltage that resulted in electrostatic deposition of particles on the surface of the tubular electrode. The second in the trend of spray drying is the vacuum spray drying. Vacuum spray drying system consists of 4 stages. There are atomization, vacuum drying, cyclone recovery, and powder collection. Figure 10 shows the process flow diagram of the vacuum spray drying process. Stage 1 is atomization. After atomization, superheated steam flow and feed flow with compressed air passes through the vacuum drying at stage 2. After vacuum drying, cyclone recovery takes place at stage 3, which is followed by vacuum suction system. After cyclone recovery, the recovered powder are collected in stage 4 at lower pressure and temperature of 45 degrees Celsius. Another trend in the spray drying is dehumidified air spray drying. Dehumidified air spray dryer is a modified spray dryer which consists of a conventional spray dryer connected to the dehumidified air drying system by a stretchy air duct. Figure 11 shows the schematic depiction of the dehumidified air spray drying system. From air dehumidifying system, dehumidified air flow through the drying chamber of the spray dryer and use as the inlet hot air for the system. The dehumidified air is supplied to the drying chamber through spray drying air inlet. The compressed air was also dehumidified before it's supplied to the nozzle. This drying method produces lower moisture content and higher bulk density of powdered product than conventional spray drying. Furthermore, it reduces outlet temperature and lower humidity of drying air that leads to smooth surface of resulting particles. In this drying system, that is dehumidified air spray drying system, the lower outlet temperature and lower humidity might also help to reduce thermal or oxidative losses of sensitive compounds. Conclusion: spray drying is a well-established and extensively used technique in many fruit and vegetable products. Inlet air temperature of 120 degrees Celsius to 180 degrees Celsius and maltodextrin concentration of 7 to 20% are the most common spray drying conditions for production of fruit and vegetable powders. The product possesses excellent quality, that is low moisture, low hygroscopicity and small particle size, and high bulk density and high glass transition temperature. The protection of the bioactive compounds was improved by using carrier agents such as maltodextrins or the combination of maltodextrin and gum arabic. In general, higher drying inlet temperature increase yield, glass transition temperature, solubility, hygroscopicity, and particle size, and reduce the moisture content, water activity, bulk density, and bioactive compounds. In contrast, addition of carrier agent enhance protection of bioactive compounds, yield, solubility, bulk density with reduced moisture and hygroscopicity. Incorporation of several new technologies into spray drying improved the quality of fruit and vegetable powder. Ultrasonic atomization provided narrow particle size distribution, protected heat-sensitive compounds from thermal loss and pressure stretch, reduced yield stretch, and improved solubility. Vacuum and controlled atmospheric drying chamber enhanced retention of bioactive compounds, and dehumidified air supply improved powder recovery, reduced moisture content, and increased the bulk density. Are the references which I use in this presentation, and hope you guys enjoyed the topic. For any clarification, let me know in the comment section below. Thank you one and all for watching my video until the end. Thank you.